Now we'll use this lemma to prove the main theorem in this section. The theorem states as follows. Let f be a polynomial in m variables over Zp, the ring of periodic integers. And let little x be a vector with m components over Zp. And we take three integers, n, k, and j, satisfying first, j is an integer from 1 to n, and k and n still satisfy the inequality as in the lemma. Now suppose this little x and little f satisfy the following two equations. First, little x is the root of little f modulo p to the power n. And the periodic valuation of the j's partial derivative of f, where j is an integer from 1 through m. The j's partial derivative of f evaluated at x satisfies as its periodic valuation is equal to k. Previously, when little f is a single variable polynomial, we just take its derivative. Now, because it's the multivariate polynomial, here we are looking at its j's partial derivative for some j. Assuming all of these, then we have there exists a 0 y of little f from Zp to the power m, a vector over Zp, which is congruent to this given little x modulo p to the power, you guess what? It has to be p to the power n minus k, same as the thing in the lemma. The theorem can be viewed as a generalization to the previous lemma in two ways. First, it generalizes the previous lemma from one variable to m variables. And second, it provides the error analysis between the true solution, meaning this y, and the approximate solution, x. The y in the lemma is not the true solution. It is still an approximate of the true solution, just a bit closer to the true solution than this x. But the y in this theorem is indeed the true solution to f. Remember, from numerical analysis, the true solution to an equation is the limit of the sequence produced by Newton's method. And the proof of this theorem also follows the same philosophy, namely the true solution y will be produced as a limit of a sequence based on the given x in the statement. Now let's prove this. We're going to begin with a case with one variable, namely when m is equal to 1. By applying the lemma above repeatedly, we're going to produce a sequence. We're first going to apply this lemma just to this x when m is equal to 1. And we call this first initial element x superscript 0. And by this lemma, we obtain another element y that is closer than this x to the true solution, which we will denote by x superscript 1. And this x1 will also satisfy these three conclusions. We'll change the order a little bit and copy them here. And now we're going to apply this lemma again to x superscript 1. And we obtain x superscript 2. But here is a little subtlety. When we change from x superscript 1 to x superscript 2, remember this x1 satisfies this f of x superscript 1 is conclude 0 modulo p to the power n plus 1. So from here to here, we're going to replace this n in the lemma by n plus 1. So every n here will be replaced by n plus 1. So this guy will become p to the power n plus 1 minus k, and this guy will become p to the power n plus 2. The new conclusions here are: first, x superscript 2 is congruent to x superscript 1 modulo p to the power n plus 1 minus k. And secondly, f of x superscript 2 is congruent to 0 modulo p to the power n plus 1 plus 1, which is n plus 2. And thirdly, the periodic valuation of the derivative of f at x superscript 2 is still equal to k. This is not changed. Now, by repeating this procedure and arguing inductively, we can construct a sequence satisfying. Now let's compare it to the case when q is equal to 1. So we have, in general, x superscript q plus 1 is congruent to x superscript q modulo p raised to the power n plus q minus k. And the second guy is f of x raised to the power q plus 1 is congruent to 0 modulo p to the power n plus q plus 1. I can also copy the third conclusion, but the third conclusion will not be used in the rest of the proof. So let's just keep the first two. This is true for all q. And actually I can replace this q plus 1 in the second line by just q. It doesn't matter. But let's just keep it in this way. Now, we observe that this sequence x superscript q will form a Cauchy sequence. And to verify this, it suffices by the previous remark we had to verify just the difference between two adjacent terms in that sequence will go to 0 as n goes to infinity. This remark corresponds to the remark on page 13 of Sarah's book. So let's just check the difference x superscript q plus 1 minus x superscript q. Their construction, their difference is a multiple of p to the power n plus q minus k. So this guy is p to the power n plus q minus k times z for some z in Zp. And the distance between these two elements under the p-adic metric, this is e to the negative Vp of this difference. And this is less than or equal to e to the power negative n plus q minus k, which decays to 0 as n goes to infinity. And this part falls from this product rule for the p-adic valuation. This is on page 12 of Sarah's book. Now by the remark on page 13 of Sarah's book, the sequence x superscript q is Cauchy. And since Zp is complete, this sequence is converted. And now we denote by y the limit of this sequence. That is false that we have two conclusions. First, we have f of y is equal to 0, meaning y is a true solution to our polynomial equation. And second, this y is congruent to x modulo p to the power n minus k. The proof for the case when m is equal to 1, the single variable case, will be completed once we verify these two conclusions. Now let's verify them. To verify first one, we need to show that f of y is congruent to 0 modulo any power of p. And to that end, because y is the limit of this sequence, we need to show a fact saying that f is continuous with respect to the topology on Zp. Given that f is a polynomial over Zp. This is not hard to see. Indeed, f is Lipschitz. And let's verify this. For any x and y in Zp, the distance between f of x and f of y, by definition, this is the e to the power negative Bp f of x minus f of y. And because f is a single variable polynomial, we can factor out an x minus y from this difference. So this difference will be equal to x minus y times some polynomial of x and y. So this g is a two-variable polynomial over the ring of periodic integers. And this guy is less than or equal to e to the power negative periodic valuation of x minus y. And the reason for this is, as before, by the fact on page 12 of Sarah's book on the periodic valuation of the product of two elements. So periodic valuation of product of two elements is equal to the sum of the periodic valuation of individual elements. And this g of xy for x and y in Zp, so this is the element in Zp, so it has a non-negative periodic valuation. So this guy must be less than or equal to this. By taking a equal to x minus y and b equal to g of x comma y. But the last term is d of x comma y. And this shows that polynomial f is Lipschitz and therefore continuous. And now because f is continuous and xq converges to y, we have that f of xq concurrent to 0 modulo p to the power n plus q. This is something we obtained from the previous. I'm just replacing q plus 1 here by q. This will imply f of y is congruent to 0 modulo p to the power n plus q. And this is a statement true for any q. And at this stage, you might get confused because the continuity of f from Zp to Zp is something without modulo p to the power n plus q. This is the continuity for the topology in the whole Zp. But this implication is indeed correct, because what we are doing here is that we are looking at the component a sub n plus q. This happens at the n plus q's component of Zp. The continuity of f from Zp to Zp in particular implies the continuity of f at the n plus q's component. So this is indeed rigorous. And furthermore, we can conclude from here that f of I is also congruent to 0 modulo the smaller powers of p. This is by the compatibility of elements in Zp. For example, when q is equal to 0, meaning f of y is congruent to 0 modulo p to the power n, implies f of y is congruent to 0 modulo pn prime for any n prime less than or equal to n. This is the compatibility in Zp. Therefore, f of y is congruent to 0 modulo any power of p, and this means f of y is 0 in Zp, which verifies the first statement here. Now let's check number 2. To show this, we notice that from the equation series x superscript 1 minus x, which is really x superscript 1 minus x superscript 0. This is congruent to 0 modulo p to the power n minus k. And in general, we have this. So let me copy it down here. Plus q. And if you add all of them together on both sides and cancel the telescoping terms, you will get x superscript q plus 1 minus x congruent to 0 modulo the smallest power, which is p to the power n minus k. And this is true for any q. Now from the last line, we write, so we can replace this q plus 1 just by q, because this is for any q. We write this difference as p to the power n minus k times y superscript q, where y superscript q is in Zp. And we make the following claim. We claim that yq converges as q goes to infinity. And to verify this, it suffices to show that this sequence is Cauchy. And by the remark on page 13 of Sarah's book, as we have already used before, it suffices to show the difference between yq plus 1 and yq will go to 0 as q goes to infinity. And to this end, we're going to look at this equation and observe that this power of p is injective on Zp. So we can divide both sides by p to the power n minus k. And as a consequence, if you look at the periodic distance between yq plus 1 and yq, this is e to the negative Vp of yq plus 1 minus yq. And we plug in this equation to here. We get the difference of xq plus 1 and xq multiplied by p to the negative n minus k. This is by the injectivity of the multiplication by Pn minus k map. So we can divide both sides by p to the negative n minus k. Or you can think of this happening in Qp. But this element is really in Zp, because this element is precisely this. And this guy is in Zp. Now, what is the periodic evaluation of this guy? By the product rule, again, this is e to the negative Vp xq plus 1 minus xq. Now plus n minus k. Now because SQ is convergent, is Cauchy. So this guy, this periodic valuation will go to infinity. So this part will go to 0. And this n minus k is fixed. So this whole thing will go to 0 as q goes to infinity. And this verifies that yq is Cauchy and therefore convergent. Now, because it's convergent, let y tilde be the limit of yq in Zp. When you take the limit of both sides, because SQ converges to y, and this YQ converges to y tilde. When you take the limit, you get this equation in Zp. Therefore, y is congruent to x modulo p to the power n minus k. The difference is divisible by p to the power n minus k. And this verifies the second conclusion. And this finishes the proof of this theorem for m equal to 1 case. Now let us deal with the general case of multivariate polynomials, namely when m is strictly bigger than 1. The case when m is bigger than 1 reduced to the case when m is equal to 1 by modifying only the jth component of the polynomial f. Specifically, what we are going to do is that we are going to define a single variable polynomial out of the original m variable polynomial f. We let f tilde be a polynomial in one variable over Zp, obtained by replacing all the indeterminates xi's where I is not equal to j by little x sub I, which are given in the hypothesis. So those little x1 through little xm are given in the hypothesis. And we're going to replace all the variables of f except for the jth component by little xi. What has been proven above for the single variable case can be exactly applied to this single variable f tilde and capital Xj equal to little xj. By what has been proven above, we can conclude that there exists a y sub j in Zp that is congruent to xj modulo p to the power n minus k, such that f of y sub j is equal to 0. This is a true solution in Zp. Yj is in Zp. And this equation also holds in Zp. This was what we proved from here. In case some of you may be confused with this sentence, let me rewrite it with a mathematical formula. The sentence means we started with a polynomial in m variables. And now we're going to replace all variables except for the jth variable by fixed values, where those fixed values are given in the hypothesis, where those little x1 through little xm are given. And we call the resulting single variable polynomial in xj f tilde. And this variable is still denoted by xj. So this is the definition for f tilde, and I hope this is clear. It's constructed from f by fixing all the m variables of little f except for the jth variable by little x1 through little xm except for little xj. xj is still a variable. And then we apply what we have proved for the single variable case to this new polynomial. And capital Xj equal to little xj. And this shows there exists a yj congruent to little xj modulo p to the power n minus k. And the little yj is a root in Zp of f tilde, the new single variable polynomial in Zp. Now we put y1 through ym to be little x1 through little xm, except for the jth component. Or for the jth component, we still use y sub j. Here, little y1 is equal to little x1 all the way to little y sub j minus 1 is equal to x sub j minus 1, y sub j plus 1 is equal to x sub j plus 1, and ym is equal to little xm. Just for the jth component, we still use this yj we just obtained. And now we claim that this with m components will satisfy. First, it is the zero of little f over Zp. And second, it is congruent to x modulo p to the power n minus k. We'll check these two things. The verification is straightforward. What is little f of y1 through ym? So we just plug in the definition for y1 through ym. This is the jth components yj, and the other components are xi's. And this is equal to f tilde of yj by our construction from here. And f tilde of yj is equal to 0 in Zp. And on the other hand, little y minus little x, this is our little y. I should write this more clearly. By construction, the only non-zero component is the jth component, where it is equal to y sub j minus x sub j. but this guy is congruent to 0 modulo p to the power n minus k. This is what we have established in the first step for the single variable case. So this is congruent to 0 modulo p to the power n minus k. So we have constructed this little y as desired. And this completes the proof of theorem 1.